Okay, today we'll be talking about different tasks of core computer vision algorithms and tasks, detection and segmentation. We will also be covering topics around visualization and understanding. I will cover the most important ones. All right, so the previous lecture, last time, what we discussed was around the topic of transitioning from sequence to sequence models, RNNs, through transformers. And we saw that transformers were defined by having some sort of encoder, a number of layers, which had multi-headed self-attention and layer norm, as well as some MLP layers. And this was ultimately called something that we now refer to as encoder, encoding the sequence. And then if we need to decode an image or a language, a sequence as the output, then similar type of architecture is used for decoder, getting the encoded tokens as input, taking those as input, and then generating what is, I'm hoping that you can see my cursor too, what is the output, the desired output. We did talk, Justin talked quite extensively about the differences of modeling sequences, recurrent neural networks, RNNs, and their variations that we've talked last week, I think on Tuesday, about, and then using convolution also as another approach. But we talked about ultimately that self-attention is what we work with in many of the applications these days. They work much better than the other two. They are more expensive. They do add computation and memory requirements for, but that comes with much better modeling of the sequence and better results in terms of any of the tasks. So until here, it was mostly talking about self-attention. We also talked a little bit about cross-attention and related topics. And then we got to the topic of vision transformers, which is one of the core models that is being used in modern applications, computer vision applications. We did go through this in the last minutes of last lecture, and the previous lecture, and I want to revisit the topic. And after that, I'll stop and hear any questions or comments you may have regarding the assignments and everything that I talked about so far. We talked about the fact that what we do with transformers when we want to process images, we split the image into patches, basically creating a kind of sequence, right? So the image was split to S by S, or in this case, maybe 3 by 3 patches. And each of those patches are then represented by what we call tokens. And tokens are often a linear projection of the vector, the reshaped version of the image into a vector, and it's basically a d-dimensional vector, as you can see in this slide. But because we have turned the image into patches, what becomes important, what are we losing here? It's basically we're losing the location, the position, the 2D position of the image, right? So that's why we often create or add something that we call positional embedding. And there are many different ways of doing this. You can create a sequence, just put numbers of sequence as 1, 2, 3, and so on. Or you can do a 2D version of X and Y coordinates. And adding these two together creates the new token that goes to the transformer layer the same way all of the self-attention, layer norm, and everything that we've talked about, NMLP, everything we talked about last week. So, and then the output layer will generate the output vectors for us, could be used for any application. One of the major applications in computer vision has been classification. We started with image classification, right? So with image classification, what becomes important is to somehow be able to encode or generate something as the output that is representative of the class. So what we do is often we add one token, a special extra input to the transformer, which is of the same dimensionality, but it's a learnable parameter that in the output space, whatever that represents is going to be turned into the class probability vector. So a C-dimensional vector, which is the class probabilities, and that's what we often call the class token. So this is one of the base and a most standard way of doing using VITs, vision transformers, for image classification. But transformers are not only used for classification, they could be used for many other tasks that we will be covering some of those today as well. But last week, we also talked about this other variant of the transformers, again, same tokens. And from the tokens, we go with the transformer layers. If you remember last time, we talked about these multiple layers of transformers. As I said, positional embeddings are added. And here, because images are, we see the entire image all together, we don't have to do masking like we did for language, because language is really a sequence that we shouldn't be using the future information for. And then ultimately, transformers give an output of a vector patch for each of the inputs. And the other option for training a transformer is actually to, instead of having a separate class token, just take the outputs, run a pooling layer, and then turn that into a probability vector for C different classes. So I talked about two versions of transformers, right? One of them was we're using a class token, and the other one was for we take all of the output tokens, we apply pooling and projection into a vector that represents the class probabilities. How we supervise this, it's the exact same thing that we talked about earlier. And that was backpropagation, defining a loss function, binary cross entropy, the soft max loss, and so on. So this was VITs. This is VITs in a nutshell. But and over the years, this type of architecture for many different applications have remained the same. Many modern architectures right now use many of these components very similar to what we presented here, but there are some optimizations that we had in the slides last week, but I think I'll just spend quickly a couple of minutes on them. But I want you to understand that there are many different tweaks and optimizations for better performance and also making the transformers, the training, a little bit more stable. One of them is actually the residual connections. This layer norm is basically outside the residual connection. So this means that whatever we get here, we normalize it, right? So this doesn't really mean that we can't replicate any form of identity function anymore that ResNets really wanted to do, right? So the solution for that is to bring in the layer normalization. We often put it before self-attention, and the second one right before the MLP layer. So normalization is there, but we also preserve our identity function. There are also other ways of normalizing. There is this RMS norm, root mean square normalization, which is actually a very basic type of normalization. It doesn't use for each of the features, it doesn't use the mean value of the feature for normalization, but this makes the training a little bit more stable. Again, these are all empirically shown to be better options. Although there are some justifications why they work well, but mostly the reason for adopting these is just the fact that they make the trainings more stable. The other option is to, instead of using a simple MLP, we use a SUGLU MLP where we actually do some sort of, this is what we call gated nonlinearity. Instead of having two vectors of weight matrices of W1 and W2, we add a third one, 1, 2, and 3. But here we create some sort of gated nonlinearity, which basically what it does is getting more trainable parameters, and not just necessarily trainable parameters, but creating a better nonlinearity for a small architecture. Even if we select the hidden layer value equal to 8D divided by 3, it keeps the same size of the network in terms of the number of parameters, but it does learn higher dimensional nonlinearities in that layer. The last piece is mixture of experts that is often used in even the very modern architectures these days. Instead of having one set of MLP layers, we can have multiple sets of MLP layers. Each of those will be an expert. And what we do is, through a router, the tokens will be routed to A of those E experts. And in this way, we actually have A active experts, but then again, what it does is it increases the number of parameters, and it helps learning more robust models without increasing too much on the compute. And these again are all parallel MLPs, so we can have multiple experts in parallel. As I said, they are used in all LLMs these days, large language models, and all of the modern LLMs up to the level that we know about are using these types of tweaks. And this is the summary of all of the tweaks that I just mentioned. This is similar to bias? No. This is completely a trainable parameter by itself that you train either a feed-forward network or just a linear projection to turn that into the probability vector. No, so it's not just bias. Then again, remember that you have so many self-attention networks here, right? So layers here, and those self-attention layers are basically fusing the information, creating attention between all of the tokens and this class token. So when you supervise it from here, the loss function comes in. This will represent the class token, the class probabilities vector. So the question is, if there are nice intuitions, what different experts are doing. That's a great question. Because they are trained in parallel and they are initialized differently, they often try to learn one aspect or a related, maybe also sometimes very much related aspect, but it's just adding more compute and more parameters, giving the network to learn different things if it does have to learn multiple concepts. For example, if you have to cover multiple probability distributions, then with these MLPs, you often have the power to separate those modes of data. So the question is, if the number of experts is a hyperparameter or not. Yes, definitely it's a hyperparameter. From what I know, it's often predefined. Don't necessarily like over fine-tune them. But yes, they are all hyperparameters. Yes, yeah, and they are terms. So why moving the layer norm helps us learn identity transformation. So look at this architecture. Will you be able to create any form of identity? Because right after that residual connection, the feature values are changed because you have a normalization. You will never have the identity in the features, right? Because right after that, you see the layer normalization, right? And that's why what we do is we bring it in. We have quite a few different tasks in computer vision. And these were the core and the most important tasks over the years for computer vision applications. Although these days we are solving much harder tasks and nobody cares about object detection anymore because now we can just do it with one line of code. But over the past 10, 15 years, there has been a lot of advances and I want to really cover some of those today, just so if you have to design something new yourself, you know where to look and how to design your models. And then ultimately there is the topic of visualization and understanding, which is very important in many applications. For example, if you're working with medical data, often the visualization or understanding is more important than the classification itself or detection of tumor, for example. You want to know where, why, and so on. And the way we started the class, and this slide is probably very much familiar to everybody. We talked about different tasks, and for object classification, for the task of classification, we talked about this. We spent quite a lot of time over the first few lectures saying how we can create a classifier that classifies images from pixels into labels. But then one of the other tasks important similarly is semantic segmentation. And within semantic segmentation, what we care about is to assign a label to every single pixel inside the image, turn each of the pixels into a label that is the label for that object or anything in the scene. So basically, when we train a model that does this, at the test time, we want to take an image and generate the same map as the output. How do we do that? There are many different options. So let's say what I can do is just look at each pixel, every single pixel, and say what the value or what the label for that pixel should be. In the very basic form, as you can see here, it's actually very much impossible. It's hard to say what pixel that represent that specific, what object that specific pixel represents, because there's no context if you only look at the pixel itself. So that's why context is important. We look at the surrounding areas, and then if I take these patches, the pixel in the center and the surrounding areas, now I can train a convolutional neural network or any network that generates the output label for us, right? It's the same architecture that we've talked about over the quarter, and you can select any of those that we used for image classification, because now you're classifying the image, the entire image. It could be a CNN, could be a ResNet, could be a VIT or whatever. This is really time consuming, because if you want to run one full network for every single pixel in an image, it will take forever to turn this into a segmentation map. The other option that we can use is to, instead of running one network for every single pixel, What if we train a neural network that takes the image as the input and outputs the entire pixel map, the segmentation map, not just one single label, a matrix of labels, right? And in that case, we will have our segmentation task solved. And in order to do that, we need to have a layer in the input that is the same size as the image. And also in the output, we also need some sort of an inflated layer. You can't go to fully connected layers and so on, because now we are generating an image. And because of that, we need to keep the network inflated. And then that's what we call often fully convolutional neural networks, or FCNs. So with fully convolutional neural networks, this is definitely a great idea, but there is a caveat, there is a problem. These images are large, and these networks, these layers will become very large, and there will be so many parameters to optimize, especially in the early years that we didn't have powerful GPUs. This was a bottleneck, a problem, a challenge for training algorithms. And that's why the algorithms evolved into starting from full-size images, going down in terms of the resolution, making the convolutions, the spatial resolutions smaller and smaller through downsampling operations. And then somewhere in the middle, we'll have a low resolution, but somehow thick in terms of the number of channels. And then from there, what we do is we go back up to the same size of the image to create the output pixel. And in order to do that, we know how to do the downsampling, right? Downsampling was easy. We've talked about it. We talked about pooling operation, strided convolution, and several other steps or operations that could be used here. But on the upsampling side, we don't really know how to do the upsampling, right? Because we don't have pooling or reverse of up pooling or reverse stride convolutions, right? And because of that, we had to invent some new operations that reverses downsampling by itself. But before I go to the upsampling, defining what upsampling is, I just briefly want to tell you that how this, maybe I can ask you a question. How do you think this network is trained? Because now we have a network that starts from an image and ends with an image. And then the tools that we have for training this network was a loss function, right? How do you think is the best to train or define a loss function for this network? We talked about softmax loss, right? We talked also about a little bit about some regression losses and SVM loss. But assuming that we want to use softmax loss function, how could we define this or train this network? What would the objective be? So you said mean classification loss for each of the pixels. And that's correct. You can add the loss function for every single pixel, because every single pixel is doing a classification, right? So you will have a sigma over all pixels of the image, and the loss function is just a simple softmax. And then you can backprop. That's the entire loss function that you need. The question is, do we need what we call ground truths for training? So that's actually the ground truths of segmentation. And yes, for these types of algorithms, because they are fully supervised, we do need the ground truths label maps. And early years, there has been a lot of work doing and sitting down and manually labeling the pixels to be able to train these algorithms. Yes. These days, we don't need that because we have tools, but early on, in order to train these algorithms, we needed the ground truth. Okay, very briefly, let me tell you what we do with upsampling. Upsampling is actually not that hard. We can use an unpooling operation. There are different ways of doing it. One is nearest neighbor. If I want to go from a 2 by 2, as an example here, a matrix to 4 by 4, I just need to copy the data kind of for each of these, take the nearest neighbor in the lower resolution one. Or bed of nails is you just select one of those in the upsampled version. You only select one of those, or the one in the corner, to copy the data, replace everything else with 0, and through multiple layers of convolution, these values will start appearing. If we used max pooling in our network, in the encoding side, what we can do is we can save the locations of the max, the ones that were selected, and then copy the data in the unpooling, max unpooling stage right over there, that the max was defined. So basically we save the locations in the encoding part, and in the decoding part, in the upsampling step, we reuse those saved coordinates. The other option is to do a learned upsampling. All of these that I showed, there is no parameter to be learned. It's just an operation. But learned upsamplings are also possible. Very simply, let's revisit the convolution. In the convolution layer, what we did was applying a convolution filter for a pixel and generating the output, and do this repeatedly for all of the pixels, right? And when we wanted to do to downsample, what we did was strided convolution, where instead of taking steps of 1, we take steps of 2 and generate the outputs step by step. If you don't remember this part, go back to the lecture we talked about it, third lecture, I think. And then we can replicate the same for the upsampling process. So this one will represent this area in the upsampled image, and then we define some weights here to map that to the output map. And then for the next one, same story, but there will be overlaps, and for the overlaps, we often sum over the values. Let me give you an example, sum over the outputs. Let me give you an example, and that's with a simple 1D function. If the input is just 2 values of A and B, we learn a filter that filter maps it to the higher resolution output, right? And for doing that, we just apply the filter to each of the values and write the outputs here. For the parts that there is an overlap, it's the summation, addition of what is coming from each of the 2 locations. So we did talk about this fully convolutional neural networks and how they are being used. These are actually some of the most basic and mostly widely used algorithms for segmentation. And I want to also very quickly highlight one of the widely used networks, UNet, as you can see the shape U. It's actually the same architecture as I showed here, just let's draw it as a similar to a U shape. And the reason that I'm highlighting this is that still today, some of the medical applications that work on segmentation, use segmentation algorithms, still this is this UNet or its variants generate the state-of-the-art results if you don't want to use any foundation model. So what it does is exactly what we explained. A downsampling phase that increases the field of view and loses some special information, and then upsampling phase that goes back to the image resolution. The only difference that UNet has is because it's used for segmentation, there is this understanding that we need to keep the special information in the decoder side, because when we downsample, we somehow lose resolution, and then upsampling, if you don't have the information, it's going to be a little bit hard, and we often get into sometimes boundaries are faded. And in order not to get there, the feature maps in the encoder side are actually copied as inputs to the decoder layers. In that way, you're keeping this structural information within the image and generate the outputs that are much sharper. So this was the idea about behind UNet, and as I said, it's actually being used quite often. Summary of semantic segmentation, what we talked about today, the fully convolutional neural networks. You have same filter as before that we had for downsampling here. So you have to save time, I actually removed some of the slides from this part, and I have it in the backup slides. You should check it out. This is a reverse, this is a transposed convolution. So we do have a 3x3 matrix here, and then instead of convolving the input image, input data, we do the convolution apply the convolution on the transposed version of the input, and it actually generates a larger output. So it's the transposed convolution. It's the reverse of the regular convolution, but why transposed? I would refer you to take a look at the additional slides. So the question is the filter trained? Yes, it's very much similar to other convolution layers. All of the filters are trained, yes. Yeah. Okay, great. This was the topic of semantic segmentation, and as we talked about this, we only get labels for the pixels. But if there are two instances of the same object, we have no idea which one is which, right? Because this is just generating or outputting the labels, pixel labels. And this brings us to the topic of instance segmentation, where now we not only care about the pixel classes, but also I want to know that these pixels belong to one instance of the dog, and this next one is actually a different dog, right? And for doing that, what we need is understanding objects, multiple objects in the image, and brings us to the topic of object detection. Object detection has been one of the, besides image classification or after image classification, has been one of the core computer vision problems and tasks. And for many years, many different algorithms were proposed for just doing the task of object detection. We are going to fly over some of them and highlight a couple of important ones. But again, there are so many works in the literature that, even in the literature of deep learning, that I'm not covering here. So in the past 10, 15 years. How we can do that and solve the problem of object detection, if it's just a single object, it means that we need to do the classification, generate a label, class scores, as well as getting a bounding box, coordinates of a box, right? So we need the coordinates of the box, x, y, and h, and w as the output, as well as what class it is, right? So this is exactly the task of object detection. How can we solve this? It's very simple, right? We can define a softmax loss function for the class scores, and we can define an L2 loss function, which is a simple distance metric, a regression loss for the box coordinates. And having these two defined, we have a multi-task loss. We are solving two tasks at the same time, and for doing that, we again add the loss values and generate a compound loss function, as you can see here. So this is simple, it's doable. If we have one single object, we can for sure solve this problem using this architecture that I talked about. But this is not that easy if we have multiple objects in the scene. So for 3 objects, we have to generate 12 output numbers. And if there are more, then it's going to be too many numbers to generate. So this algorithm is not really scalable. It's just extending the classification into some sort of object detection, which is fine, but it's not really scalable. So when there are multiple objects, one solution is instead of going or getting the entire image as the input, why not to look at bounding boxes? For each bounding box, we can say we only have one label, and whether it's a cat or a dog or the background, right? And if I have this way of classifying each of the bounding boxes, I can do a sliding window. I can create just bounding boxes, slide it over the image from coordinate 0, 0 to all combination of x, y, and h and w, and see if we can detect the object. So step by step, I can create, I can find the bounding boxes that have the maximum probability of each of the objects. But there is a huge problem here, right? Again, there are so many different combinations of bounding boxes that we can use. And again, this algorithm is not scalable. What we've been doing in the literature, again, early years, if you look at the years these articles were published, 2014 and before, there has been a lot of research around finding regions that are, they have high probability of having the object in them. So region proposals. And if I have a way to find region proposals, that's actually going to be an easy-ish problem. I can do the same thing as I explained earlier, right? For an image, what we can do is if I have region proposals, I can just take that part, that patch out, and run a CNN on that patch, right? And convolutional neural network on the patch, and then classify it. And in order to even I can refine the bounding boxes. So classify, and then refine the bounding boxes to have the object detected. So we can classify the boxes and also refine the bounding boxes if I have to change the coordinates a little bit. And this is what is called RCNN algorithm. And although it works, and again, this is one of the early algorithms, CVPR 2014. These are very slow because for each of these boxes, again, we are running a full convolutional neural network. But there is one catch that what we can do is instead of running convolutional neural network on each of these boxes, because convolutional operations, they preserve the special information, right? They either downsample or upsample. We always have a way to track them where in the pixel space they are, right? So in that case, what we do is instead of running the convolutional neural network on the patches, let's say we run one big convolution on the entire image, and then now we have the regions in that feature map, which is corresponding to the entire image. Let's look at those regions and now run a smaller CNN on top of those and generate the outputs for each of these two outputs that I want. First, the box offset, like should I move the bounding box a little bit, or what the object category is. So this is the fast version of our CNN. These are some basic algorithms that we can use convolutional neural networks for detecting objects, their bounding boxes, and so on. The question is if the number of proposed regions are predefined. The short answer to that is yes. I will talk very briefly about the region proposal networks too. So easy algorithms, right? One puts the bounding boxes of the regions, the proposed regions, on the images. One puts it on the feature maps of the ConvNet. And both of those generate the output class label as well as offset of improving the location of the detected object. But this requires us to do that bounding box region proposal first and have a region proposal network that tells us where in the image we should look for. And there has been research on building region proposal networks, RPNs. And here what we do is we just randomly start with the CNN. We try to randomly start in different locations in the image, and through layers of convolution, we refine those regions where they have the higher probability of having an object in them, because we have the object labels and locations, so we can supervise this, and then each of those also refine the box coordinates. So basically, a region proposal network, what it does is it refines the boxes, each of those boxes that have a high probability of an object in them, and the box, the output boxes, the box corrections. Again, I'm leaving all of the details about the coordinates and all of these dimensionalities for you to check afterwards, because it will take too much time, and we don't want to spend too much time on this algorithm. But what's important here is, back to your question, we often take the top K, the ones that have the highest probability of having an object in them, as the proposals for this image. This is a simple image, so then most of and only has one object, so most of the regions are centered around that single object. But in general, that's not the case. So in many setups, we can have region proposals used in different setups. We can get different objects and with higher probabilities. With that, and after talking a little bit about RCNN and mask RCNN, which again, for you, it's important to go through the details, and if you can spend some time doing the calculations yourself, that would be very good. But those types of algorithms, RCNN, mask RCNN, they're not being used anymore these days because they are very heavy computationally. Although it's important to understand how we got to this point, but those are for many reasons. One of those reasons is that we need two separate networks, one region proposal network and then one classification and box refinement network. So it's like at least two passes for detecting objects for each image, right? And that's why there has been advances after these using single stage object detectors, SSDs, and one of the most popular ones is called YOLO. YOLO is probably, if you work with any computer vision problem, you've heard about YOLO. Even to date, although it's a convolution heavy network today, at least its earlier versions. In many even industrial applications, YOLO is being used as the base for object detection because it's a fast object detector, and it's very good in terms of detecting the objects. What YOLO does, I want to very briefly tell you a little bit about. It's basically you look only once with one single pass on the image. You generate all of the bounding boxes. How it does it is it divides the image into S by S, grid of S by S. And in this example, it's 7 by 7. What happens is that for each single box in that grid, it tries to output, it creates a fully convolutional network that outputs the probability of an object being in that location, refinements of the bounding boxes. So it generates B bounding boxes and new hyperparameters. B bounding boxes, that is the refinement of the object that is present in that box. And also it generates a probability, the class probability, object class probabilities. And in this case, for example, if it's B equal to 2, it generates just 2 bounding boxes with different probabilities. It does this for all of the boxes at the same time. So basically it's the same network that is being generating something as the output for each of these bounding boxes, and it does generate a number of different options for the object. And as I said, each of those boxes are associated with a probability. And in this example, the probability is shown with the weight of the edges in each of those boxes. And for these many different bounding boxes and object probabilities, now we can do thresholding. And also, there is an algorithm that they used in the paper. Again, I don't want to go into the details, non-maximal suppression, and some algorithms with thresholding involved that identifies the ones that have the highest probabilities. So this is a simple implementation or use of the object detection. Again, this is something very useful. If you have time, spend time with the repositories of YOLO. There are so many different newer versions of YOLO that is being used for many applications in medicine, robotics, and also in many industrial applications. So the question is, how do we get this second image, and what's the intuition behind it, right? As I said, for each of the grids, we generate B bounding boxes. Like for this one, we generated 2. For all others, we also generate 2. This B is again a probability vector. And each of these boxes are associated with probability of existing an object in them. And then if I put all of them together for all of the patches, I have so many boxes. And now each of those are associated with a probability, right? Perfect. Let's move on. And one of the more recent approaches for object detection is DETR, a detection transformer. This is purely based on transformers. And the topic that we did discuss last week, and also I started today, same type of self-attention and cross-attention modules could also generate some object detections and bounding boxes for us. And how this works, this is actually another very old paper, 2020, almost 5 years ago, although it's now kind of deprecated. Nobody uses this for real applications, but it's a very good example of how to use transformers for object detection. And what we do here is basically similar to what we've explained earlier. We turn the image into patches, and then those patches are passed through CNNs, creating a token. Then we add positional encoding the same way that I explained to the patches, and those define our tokens for the input, which are inputs to the transformer encoder. A transformer encoder, again, a bunch of self-attention, layer normalization or any normalization, as well as MLP layers that generates the output tokens after multiple layers of transformer encoder. Then in order to generate the bounding boxes, this is the smart part for this algorithm, that it does take the encoder output tokens as input in the transformer decoder, but we also define some queries, which are trainable parameters themselves, that each of those, for example, if I add five queries as input, 4 queries as input, or 10 or 20 queries as input, I'm seeking up to 20 objects to be detected in that image. And then again, through a combination of self-attention layers in the beginning of this transformer decoder, as well as cross-attention with the encoder output. So cross-attention and self-attention networks, layers, it generates the output values for each of these queries, which are passed through an FFN, feed-forward network, to generate either class labels and the bounding boxes very similar to what we discussed earlier, or even in some cases it just says there is no object to be detected, and at the end we have the bounding boxes and the classes associated with bounding boxes as the output. So the question is, are we inputting every possible box to the transformer? No. The input here are some trainable parameters that are representing, they are queries representing, asking the question that I actually want an object to be outputted in place of this input query, right? So there is no box or anything as the input. It's part of the output that it generates the class label and the box coordinates. So the question is if the queries are formed in a way that it actually represents what we want to look for and where in the image, right? So in this case, what we are looking for is defined by class labels, which are defined, predefined, and they are as a part of the output. So our supervision is based on the class labels. We have a class probability vector. Same way that we defined it for the other algorithms, right? So that's how the algorithm knows what type of classes to look for. And then in terms of the outputs, again, these outputs are supervised, if you remember, based on the L2 norm, L2 loss of the ground truth boxes, right? So we are not telling anything in the query part what to or where to look for any of the objects. The training, the process itself is backpropagating. If there are any losses, any errors, it backpropagates the outputs. So basically, it's we are not determining anything in the beginning or in this part. So the question was, the query is give me up to 9 objects, and yes, that's basically what this means. And through the self-attention and cross-attention, it will try to generate output tokens that are turned into class and box coordinates through that FFN operation. Your question is if the query is over there, if they are image patches or not? Yeah. No, they are not image patches. They're just queries for trainable parameters you put them in to generate the outputs. For each of the inputs, you get the value as the output, and that value is turned into class and box coordinates. Again, the question is what is object queries? They are trainable, learnable parameters. So you initialize them, the network finds the best values for them, and that's what you get as the output. The question is if there is any intuition which FFN gets which box, right? The short answer to that is no. There's nothing that stops the network from, we are not including anything that stops the network from generating multiple, but remember that there are so many self-attention and cross-attention layers over there that they are actually interacting with each other and makes each of those queries match with one of the output layers. So it's not generating the exact same thing as the output. And we also have control over how to supervising those FFNs as well. So your question is if there are image segmentations, pixel level segmentations as part of the training. This algorithm does not require the segment level, pixel level segmentations. It's only supervised based on class labels and bounding boxes. But if you have the pixel level segmentations, you can always turn the pixel level segmentations into a bounding box to train this algorithm, right? But it doesn't necessarily require that. So the question is if it's possible to generalize unseen objects. And by unseen, you mean a new class label? For these types of algorithms that they are fully supervised, often there is no way, because you are creating class probability vector, there's no way of like adding something at the end for a new class without previously knowing there's some other classes, right? So fully supervised networks, they are often, there's no new object. We can have a background object or no object. As you can see, we have the label of no object. But there are many algorithms and mixed extensions of these types of algorithms that are used for zero-shot learning. Zero-shot means understanding something new without having an example of those in the training data. But it's beyond this topic. What happens if you have more objects in the scene than what you put in as the query, right? So that's a great question. It often generates the ones that has the highest confidence on the object, so bounding boxes with the highest confidence. And in those cases, you often want to add more queries just so you can get more objects, right? Okay, I'll be here to answer questions if you have any after the class, but we have a bunch of other topics to cover, and I want to make sure we go over them. At least you get familiar with the topics. So with the object detections, now back to the question that was asked earlier, how can we use those types of algorithms for instance segmentation? And that's actually not too hard. We talked about this when we were talking about our CNN algorithms, where we run a CNN on the image, then we have a region proposal network that gives us the bounding boxes, and those bounding boxes are turned into either class labels and bounding box refinements, right? So this is what we've talked so far with RCNN and so on. Now we can turn this into a mask RCNN that also generates the mask. So basically, same architecture that we talked about earlier. Now we can take one more output, make it more multitask, and generate the mask predictions. So what we used to be doing before was, again, image, region proposals, CNN gives us class label and the box coordinates. Now we add another layer of convolution that generates the mask, the mask for that object in the pixel level. And that mask, again, could be the same size as the input and the image. And basically on the layer itself, if we use fully convolutional neural networks, that's what we often get as the output. For each of the objects, when we have that box, tiny box, we can always get the mask for that. The chair, in different settings of the box itself, if you have different boxes, the bed, and the human, the baby in the image. And this is an extension of the RCNN algorithm, which we call mask RCNN. And with mask RCNN, it's actually the results have been very, very good in detecting different objects, different known objects that we could train the algorithms for. And then there are so many APIs and open source versions of object detectors that you can explore. There are some links and resources here, but this all basically rounds up and summarizes some of the tasks that we wanted to cover, and they are actually very important for you to understand these tasks. They have been core computer vision tasks, although these days computer vision is way more advanced. They're not bound to these tasks. But if you have industrial applications of, for example, quality control of separating rotten tomatoes and good tomatoes in an industrial pipeline, then with computer vision, you need to be able to detect objects and then classify them into good or bad, right? So that's why it's important to still understand and know these steps and pipelines and how to do them in real time. But now there are larger scale models that you're all familiar with. This summarizes the first part, the computer vision tasks that I wanted to talk about. And the last piece that I want to spend 10 minutes on is around visualization and understanding. Again, this has been a big lecture by itself. And in 2050s, 60s until 2020s, the topic of computer, and even before that, 2014, 13, the topic of visualizing neural networks has been very hot and very much, it helped us gain understanding into what the networks are learning. And I'm going to summarize some of those, the most important ones here, that you may need to use in your applications. But before that, let me go back to the linear classifier that we talked about. We spent quite a lot of time on linear classifiers. And with the linear classifiers, what we did was, at the end, we said, if I look at the linear function, what the network is learning, I can have a template for each of those classes. Like, for example, for this car, you can always see a front-facing car as a template, right? We can do the same with neural networks. If I visualize one of the filters, so here we visualize the weights of the linear function, it was the visual viewpoint. I can do the same with with visualizing the filters in the neural networks. So for each of the filters, the network is, for example, is learning something that is basically some of the basic shapes, orientations or simple shapes, as you can see here. Although this visualization we can only do it for the layers that we have few channels. Like, for example, if we have three channels, I can put them in an RGB image and just visualize it. But as you remember, in CNNs, that was not the case. In CNNs, we had different, sometimes quite a few channels in the middle layer. So it's not easy to visualize those in something that we can see, but that's what you basically see. In earlier layers that we have fewer channels, we can visualize them and see the network is actually learning some patterns. So it starts learning patterns, and then later stages, it gets more holistic and bigger patterns as if we train, if we run something that we call guided backpropagation, we can also visualize those, but not as simple as this. I want to highlight a couple of ways of understanding and visualizing the neural networks, which are actually kind of important. One is the concept of saliencies. So in many applications, it's very important for you to know which pixel matters. For example, in a medical application, when you do a classification of tumor versus none, you want to see which parts of that image is actually the tumor. Because if you want to automate this, nobody cares about knowing if there is tumor or not. Everybody cares about where in the image the tumor is, right? So in order to do that, simplest application is we train a network, a feed-forward neural network that generates the value or the class label dog. But what we can do is we can, actually, before I show you that, in this case, in order to train this network, what we've done was we always took the derivative of the neural network, the weights, of the loss or of the class score with respect to the weights in order to update the weights, right? Now what I need is for each pixel, I want to see how much changing the pixel value would affect the dog score, right? What does this mean? What I explained is the meaning of derivation, right? So if this means that the meaning of basically gradient. So if I take the gradient of the score with respect to now the pixel values, not the network weights anymore. With pixel values, I can visualize those gradients. And visualizing those means that these are the pixels that matter. In order to classify dog on this image, those are the pixels that matter. So if I change the values of those pixels, the dog score will be changed, right? Again, this is the basic meaning and definition of gradients that we've talked about. So this is one way. If you run this on different objects that you've trained in the network, then this is what you get. So that's one way of understanding saliency, and it's very effective in many cases. But sometimes it's not just about the pixel values all the way to the back. You want to see for each of the classes how the activations work. And this brings us to class activation maps or CAM algorithm, class activation mapping. CAM or GradCAM that I'll talk about in 2 minutes are one of the most and widely used algorithms for understanding CNNs, and also could be used for other architectures too. But for transformers, we have a much better way of making sense of those, which actually we talked in the last lecture. So what happens is that for each of the convolution layers, we often do pooling, and the pooling generates feature maps. The feature maps are then turned into scores, and those scores with those values of the weights, if we extend the math, basically we simply can highlight the class scores in a weighted sum form, and this means that we can trace back class predictions all the way back to the feature maps and specific locations of the space, because convolution layers are always mapped to a space in the image space too, right? We do convolution, as the special consistency across all of the operations can help us trace back all the way to the image space. So anyways, we can look at the feature maps and see how the class activations, each of these classes, are actually impacting those locations in the image. And with that, now if I do this multiplication of weights versus the weights that we've learned on top of the feature values, we create some class activations. And this means that I have a way now to go back to the image space, because as long as I'm in the convolutional space, I can go all the way back to the image and create these maps of, like, for example, for each of the classes, palace, dome, church, altar, and monastery, we can have different class activation maps these are the weights, these are the pixels or areas of the convolution layer that have been driving the scores for these specific classes. It's the same for others, like class activation maps for one single object in different images. But there is a problem with this, and that problem is that we can only apply this to the last convolution layer because this is the only way we can do it. Like, we can only go to the last convolution layer the way that we did the calculations here. And in order to solve that problem, there is one variant of the algorithm called GradCam. So gradient weighted class activation maps. It's basically the same algorithm, just we need to calculate the weights with respect to we basically take one of the layers that created some sort of activation in the class level. We compute the gradients instead of just calculating the multiplication between W and feature. We go all the way back with the gradients and create a weight based on the gradients. And then that is used instead of the weights. It's aggregate of all of the weights and gradients up to that specific layer. And then we weight that with that. And then we also use ReLU to only map, to pass the positive ones. And then that could also be all the way shown in the class, in the image space. So I talked about CAM, which was only applied to the last convolution layer. If you want to, but this is not possible because in most of the CNN algorithms, we don't have just like one convolution layer at the end, right? We always have some operations fully connected and so on. So in order to be able to carry this class activation to the convolution layer, if there is something else in the middle, we often use the gradients and basically weigh the maps with the gradients aggregates, and then we can actually do the visualization. They create these heat maps for each of the objects. So this was about CNNs, but we talked about transformers last week, right? In the last lecture, that they inherently come with the activation maps. Do you remember that language matrix that Justin showed? That for each of the output words, there is a tension weight for the input. We can do that the same thing for the pixels. For each of the outputs, we can create these maps in the pixel space and visualize the features of the VITs in the pixel space. So basically with VITs and transformers, this is much easier. We already have a way to visualize the attentions, the weights, but with CNNs, we often use GradCam or these types of algorithms. That said, I did this task that I thought I wouldn't be able to, completing the topics I wanted to talk about today. And next session, we'll have the lecture around video understanding. Thank you.